Hello there, Calc kids. Welcome back to another lesson in calculus. This is Mr. Bean, and today's lesson is on continuity. Let's start off with a really clear and basic explanation. This is going to be so easy, this first part, you could explain this to a little brother or sister, or even to Mr. Brust. He's going to understand this after this part of the lesson. So here we go. You just take your pen or pencil, and if you can trace a function, if you can just draw it, and you never have to lift up your pencil, it is continuous. Okay, that's like the really quick, easy way of saying a function is continuous. In other words, here you see, if I'm graphing this thing, I have to lift up my pencil off the screen to get this up here and then to continue drawing it. So if you have to lift up your pencil, it is not continuous. Let's do a formal definition of continuity. So if a function is continuous at some x value, we're going to call this specific x value c, then there's got to be three conditions that it meets. The first one is that f of c is defined. Okay, what is that? That just means that c exists, that c is in, you're allowed to plug c into the function. Next thing is that the limit exists at that c value. So as we approach c, there is a limit. And then the very last condition is that the limit is equal to f of c. In other words, number one is equal to number two. Those two things must be the same. So if I have, I don't know, if I'm going like this, I have some function here, and I'm approaching this limit right there, that there c is defined. So this, we'll just say that this is the c value. C is defined, the limit exists, and the limit, as they're coming together right here from the left side and the right side, is equal to f of c. That's all this means. If you understand this one, honestly, pat yourself on the back because you're understanding limits and you're starting to think like a mathematician with these crazy terminologies, so good job. All right, continuous function or continuous on its domain. I'll explain what that means here in just, I was pointing to the screen, you couldn't see me. I'll explain what this means in just a second. What I want you to do is pause this video right now and write out what type of function each of these are. Okay, I'll give you the first one. The first one is a polynomial. Yes, it was a cubic specifically, but I'm going to do a broader group than just a cubic, and that is a polynomial. Okay, see if you can come up with the names of these. So write those out real fast. So the first one here, the second one I put down as it's a rational. Some of you might have put reciprocal. That could be the same thing, a rational function. Next one would be a power function, although if you're really good at this one, you might have said that it's a square root, but technically a square root function, when we raise it to the 1/2, that's a square root. This is actually a power function, so square root's just an example of a power function. Next one is exponential function. Next one is a logarithmic function. Those two are like inverses of each other. And then the last one, you might have put sine or cosine, but it's a trigonometric, I spelled that wrong, trigonometric, there's an O in there, function. All right, so what does this mean? These functions are all continuous on their domain, meaning that where the graphs exist, they are continuous. That's not the same thing as saying that it's a continuous function. This first one's a continuous function because there's no breaks. This one's not a continuous function because you see here you have a vertical asymptote and it jumps. You have to lift up your pencil. Okay, the power function is continuous on its domain, but the domain is not all real numbers. So that's kind of a weird one because there's no graph that exists over here. There's blah, 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 there's nothing over there. So it's continuous where the graph exists. It's kind of an interesting one. Same with logarithmic. So there is a difference between saying a continuous function or a function that's continuous on its domain. So just make sure. And the first two are great examples of that. Polynomials are continuous functions. Rational functions are continuous on their domain, meaning if the graph doesn't exist there, then it's not continuous there. So what types of discontinuities exist? The first type of discontinuity is a hole. In other words, a removable discontinuity. So let's draw a quick little graph. So you got something like that, you got a hole, and then the graph continues. Okay, that would be a removable discontinuity or a hole. Next one, discontinuity due to a vertical asymptote. So if we wanted to draw a graph of this one, then we might show something that goes like this and something that goes like this. And then you got a line that separates it right down the middle, and I'll just use this green line. And so that is, if I made it vertical, that would be a vertical asymptote. That was horrible. There we go. So that's a vertical asymptote, a continuity due to a vertical asymptote, I should say. Okay, next one is a jump discontinuity. That's real simple. Usually you'll see these in piecewise functions, although they're not the only place you'll see them. So you might have a function here. I'll go ahead and fill in that dot, and then it jumps, and it's up here. Ooh, that was a big circle. And then it goes down here. So that would be a jump discontinuity where you have to lift up your pencil and it jumps straight up or straight down. So get those written down if you don't have them all, and then we'll continue on and identify how to find a discontinuity if you don't see the graph. So where is there possibly a discontinuity in this thing? It's going to be where the denominator equals 0. But in order to do this correctly, we're going to have to factor this thing out. So I'm going to take this fraction and rewrite it in its factored form. So let me skip to that. All right, there's the factored form. Now, what do we do with this? What we're looking at is that this is going to simplify. When a factor cancels, that is considered a removable discontinuity. We are removing it from the function. So when they cancel like that, that means we have, let's write this out. I'm going to write down that we have a hole, which is the same thing as saying removable. We have a hole at x equals 2. So on the graph, if you were to go to x value of x equals 2, you would just have an open circle right there on the graph. Now what about this part? Since the x plus 5 does not factor, then we're going to have a vertical asymptote. So let's abbreviate that. If you need to write that in your notes full on what VA means, it's a vertical asymptote. We have a vertical asymptote at x equals -5. Okay, hopefully that is a review from some of your pre-calc or Algebra 2 classes, but just in case, I want to make sure we covered that part of it. The x minus 6 means nothing to us. We do not care about anything that doesn't cancel out. We just are worried about when the denominator equals 0. On number 2, this one's a little weird because if you remember the square root, I'm going to come down here. You don't need to write this in your notes. The square root graphs look something like this. Okay, so there's a square root graph where we start off and you go off to the right forever. There's not really a discontinuity on this thing, right? It's continuous on its domain. So what we're going to say on this one is it is continuous on its domain. Now I will tell you, I have seen some calculus books out there that will say that it is discontinuous. This seems weird to me, but let me show you what they say sometimes. Discontinuous on the interval. So then we say wherever this thing doesn't exist. So if we solved that thing, if we said, okay, if this is negative, so if we said that it was less than 0 and solved it, you'd get when x is less than, add the 3, divide by 2. So 3 halves. That it's discontinuous on the interval x is less than 3 halves. Sometimes I see this in some books, but so you know, it's just basically saying the graph doesn't even exist there, so it's discontinuous on the entire interval. That seems kind of dumb to me. I would just say it's continuous on its domain, and then you'd have to probably say, maybe I should sneak this in here, that its domain is when x is greater than or equal to 3 halves. Okay, so it's kind of these two things are tied together right there. All right, last one. Now when we have a piecewise function, we're trying to figure out what's going on here. So this function is continuous. It's just a parabola. This one's continuous. That's a linear function, so we make a line. And then this is exponential function, and it is continuous. So all three of these things are continuous functions with no breaks. That's important to recognize first. Now let's find out if at these x values, when we get to -1, if these two pieces, so we stop at -1 and then this one starts at -1. This one's, whoops, whoa, craziness. Okay, get rid of that. This one ends at 2 and then the third piece starts at 2. So at these places where they stop and start, are they the same thing? So let's plug in a -1 into this first piece. Okay, let's see. We're going to plug in that -1 here. This is, again, is going into the very first piece. -1 plus 1. Simplify this all out and we get 1 plus 2 is 3 plus 1 is 4. All right, so the first piece is going to equal 4 here. What about the second piece? if we plug in a -1 there, -1 plus 2 is 1. So the first piece y value is going to approach 1 from the left, and if we approach -1, if we approach -1 from the right side, this piece is going to equal 1. So you have something going on like this, going on like that. Okay, so it's a y value of 1 and a y value of 4 up here. That is considered a jump discontinuity. So the way we do this, and I really didn't leave you enough room, so let's just move that up, make it a little bit smaller, and then we get a jump discontinuity at x equals -1. Remember, we're focusing on the x value. At this x value of -1 jumps from the first piece to the second piece. That's the jump discontinuity. Okay, now let's plug in the number 2. So if we plug in a 2 to this second piece, you can see you have 2 plus 2, so that equals 4. If you plug in the 2 into the third piece, you have 2 raised to the 2, which also equals 4. And so on that one, since the two y values are the same, it's actually continuous between these two pieces. They're coming together at the exact same y value of 4. So there's no discontinuity there. So this jump discontinuity at x equals -1 is the only discontinuity for that function. Now finding the domain. We've done this in the past. You've probably practiced this a lot, but we've got to remind ourselves just a little bit how to do that. And that is, usually you're just going to have two scenarios that you're really watching out for: denominators and radicals. You're looking for when is the restriction on the domain. So denominators, remember, you can't have a denominator equal 0. I mean, you got to be careful. Look what happens if your denominator is 0. So what we do is we say, what's the restriction here? I'm going to say x plus 1 is not allowed to be 0. So let's just solve that. If x plus 1 equals 0, then that would be x equals -1. So x equals -1 is our restriction for this function, but that's the only restriction. So the domain of this, we're going to say it's all real numbers except that x cannot equal -1. Okay, so that's the domain right there of this function. Second one, radicals. Radicals cannot be negative. So what we're going to say to set up the domain, we'll just say take anything that's underneath a radical. In this case, it's 7x plus 3. And you're going to say that has to be greater than or equal to 0. And then you solve it. And what do you end up with? X is greater than or equal to -3/7. That is the domain for this radical. So that's the x values that you're allowed to plug in. Okay, so let's do a couple practice ones that are a little bit more challenging than that. Finding the domain of something crazy like this. If we were trying to find a discontinuity, you can see here that that x and that x cancel, so that's a whole. But that's not finding the domain. That's just if we wanted to find discontinuities. They're similar, but not exactly the same. So we have two things going on here. We have a denominator and a radical. So let's see, this x cannot equal 0. And then the x plus 5, that whole thing is also not allowed to be 0. So x plus 5, technically it's radical x plus 5, is not allowed to equal 0. And then when you solve this, you'll end up with that x cannot equal -5. Okay, you see how I've done that? And then the last thing is whatever's underneath the radical, which in this case is x plus 5, has to be greater than or equal to 0. Okay, well, I'll go ahead and put that. X plus 5 is greater than or equal to 0. You solve that and you get x has to be greater than or equal to -5. So now we combine these three things. We say that x cannot equal 0. X cannot equal -5, but x has to be greater than or equal to -5. Well, it can't be or equal to -5 because we just said right here that it can't equal -5. So the domain of this thing is that x is greater than -5, but it also cannot equal 0. So this is the domain of that function. Okay, so you just look for when is the denominator going to be 0. That's the restriction. And it can't be negative under there. So why don't you pause the video right now, pause this thing, and I'm going to have the work show up here in just a minute. You try this one on your own. And there's the answer that I came up with, that x has to be greater than or equal to 0, but it can't equal 4. So you just take the entire denominator, say that it can't equal 0, solve it, and then whatever's underneath the radical has to be greater than or equal to 0. And then you just check out your answers and your restrictions, and there you go. Okay, intermediate value theorem, and I think that's the end of our lesson. Yeah, it is. So intermediate value theorem, this is actually really simple stuff, but we will refer to it quite a bit throughout the year in calculus, and it's dealing with some continuous functions. So here's what I want you to put on your notes. Actually, don't sketch this whole thing, but I'll save this part. Don't draw this. I just wanted you to think, I'm taking a cubic function. So this cubic function, I want to focus in on just a very specific piece. So you see this piece in blue here. So what I want you to do is just graph the blue portion, just anywhere like this. Just sketch something that looks something like that in anywhere in this quadrant. Okay, so again, this is just a portion of this entire cubic function. Now what we'll do is we're going to label some parts. So we'll label this beginning x value at the beginning of this interval, we'll call this a. And the end, where this little segment of the cubic function ends, we will call it b. So we're focusing on the interval from a to b. And you remember that goes like this, a to b, if you remember the interval notation. All right, then what is the y value of this point right here? The y value is a plugged into the function f. So we don't know what a is, therefore we're not going to know what y is, but we do know it's f of a. So what is the y value of this thing? Yes, that's right, f of b. So now we have all of these pretty lines and colors, and you probably don't have the colors on your paper, but that's okay. Just kind of sketch this out. And now with this picture, we can come up with what's called the intermediate value theorem. If f is continuous from a to b, okay, so we know that there's no break. So if we can say that it's continuous, then every value between f of a and f of b has to exist at some point. Okay, so it's going to show up at least once, sometimes more than once, but it has to exist at least once. That seems like no duh common sense. I mean, really, we have to have a whole theorem for that? Yeah, we do. But it's just common sense that if you have a continuous function that you're never going to lift your pencil from a to b, then that means all of the y values from f of a to f of b have to exist. Okay, that's actually a really important theorem that we're going to use throughout several things that we do. That if you need to know, does this y value ever show up? Yeah, it has to. We may not know exactly where, but we know it has to show up. So let me give an example of the most common time when something like this happens. We're going to use intermediate value theorem to answer just a few questions here. So here's a function, x cubed minus 2x minus 5. Let's find f of 1. So if I plug in a 1, I'm going to get 1 cubed, which is 1, minus 2 times 1, which is 2, minus 5. So what does that equal? Negative 6. Okay, negative 6. Next one, plug in a 2. 2 cubed is 8, minus 4, minus a 5. And what is that going to equal? 8 minus 4 is 4. 4 minus 1 is negative 1. F of 3, plug in a 3, you get 3 cubed is 27. And that's minus 6. And then that's minus 5, 16. Why did we do this? It's to answer the last question. Does the function have a 0? How do you know? Does the function have a 0? What does that mean? It means does the function f of x, is it ever going to equal 0? Or in other words, is it ever going to cross the x-axis? Okay, so based off of this information, yes it does, because we have a negative 1 here and a y value of 16. So let's just write this whole sentence out. According, oh, I'm going to type this. Forget handwriting. Haha, yeah, this is better. According to the intermediate value theorem. What? What according to that? How do we say this? According to the intermediate value theorem, I should have probably put at the very beginning of the problem that this is continuous, because you have to know it's continuous, but we already stated earlier in the notes that polynomial functions are continuous. So, because the IVT, intermediate value theorem, only works if it's a continuous function. So, according to the intermediate value theorem, there is a 0 because f of 2 equals negative 1 and f of 3 equals 16. Therefore, what else can we say? There must be a 0 between x equals 2 and x equals 3. See, because the sign changes. So when the sign changes, it had to have crossed the 0 at some point. So if we were at -1 and then we went to 16, then the 0 exists somewhere in between 2 and 3. All right, that is an extremely important theorem for us, but that is the end of our lesson. Hopefully that wasn't too bad for you. Rock that mastery check, and congratulations on finishing unit number 1.